join me in welcoming to the Distinctive Voices podium, Tracy Drain.
Hello, everyone. I'm delighted to see you all here today. Glad that there's some students in here, too. I'm going to include a little bit in this presentation about how I wound up doing the kind of job that I'm doing now. So I'd love to see young folks who might put some of that same stuff to use. So without further ado, we're going to get started. This is an image of the Jet Propulsion Laboratory. It's only about 50 or so miles from here, so maybe some of you guys have visited it before. It is located in the foothills of the San Gabriel Mountains near Pasadena, California. Way back in the 1930s, a group of Caltech students called the Suicide Squad were trying to build rockets at Caltech campus. And after one too many malfunctions, they politely asked them to leave campus and sent them out to this uninhabited arroyo so that they can go do their tests without having to potentially harm anyone who's nearby. They had their first successful stand-up rocket test in 1936 on Halloween, and then over the years, it developed into what is now the Jet Propulsion Laboratory, a huge lab, one of the 10 NASA field centers across the United States. There's about 150 buildings, over 177 acres, about 6,000 employees work there, and it has become one of NASA's centers for robotic exploration of the solar system. So just a few highlights. Back in 1958, the Jet Propulsion Laboratory helped build and launch and operate Explorer-1, which is the United States' very first satellite that we put in orbit around the Earth. It discovered the Van Allen radiation belts. You might recognize a few other of the spacecraft here. This is Voyager, Voyagers 1 and 2, that visited our gas planets, and now both of them are off into interstellar space. This is Cassini, which orbited Saturn for 13 years and had a fantastic wrap-up to its mission with a really dramatic, they don't like to say crash, controlled deorbit into the planet of Saturn in 2017. This is Curiosity rover, which some of you guys might recognize. Right now, the lab operates something like 20 spacecraft and about 8 major instruments active right now. So a lot of stuff going on at the lab. So how did I wind up working there? I grew up in Louisville, Kentucky. That's me, little baby Tracy, with my brother, my older brother. Luckily for me, my older brother was into sports. He was a fairly popular kid. He kept all the other kids from picking on me too much for being super nerdy, because I was that kid who was always stuck in a corner reading books, playing my instrument. Loved math and science. This is me in the band. And my lovely mother supported me in all the things that I was interested in. She bought us lots of books. Those of you who remember the World Book Encyclopedia, way back before we had Wikipedia, my mom bought us these childcraft books to go along with those. And I remember for the first time reading the story of how scientists think the solar system was formed from a huge cloud of gas and dust that came together and formed our sun and all of the planets. I was pretty amazed that scientists could look up at the clues around us and piece together a story of something that happened 4.5 billion years ago. There weren't people around with camcorders to let us know what was going on. I also loved science fiction. I read lots of Isaac Asimov and Robert Heinlein and Douglas Adams, all the greats. And my mom loved watching science fiction. She raised us on Star Trek, the original. I really love The Next Generation. We watched Star Wars, Battlestar Galactica, all of the sci-fi shows and movies you could think of, we watched them. And when I was in school trying to decide what I wanted to study in college, I really wanted something that would let me be involved in space exploration, so I could be part of the people trying to make the world look like those things that I saw in the science fiction TV shows and movies that we watched all the time. We didn't have the internet back then, I am that old, and I didn't actually know what it was that astronomers did. And so I decided to study engineering because I knew I could at least build tools that astronomers and scientists could use to go and study the world. So I studied mechanical engineering at the University of Kentucky. I was very fortunate to land an internship at NASA Langley. For the students in the room and watching, definitely do internships while you're in school. It's a great way to decide whether you like the thing you're studying and you really want to do that for the rest of your career, or if you want to try something else. I really loved what I was doing and decided to go to Georgia Tech to get my master's degree in mechanical engineering. To be honest, I didn't quite feel ready to be unleashed on the world as a baby engineer. I wasn't done cooking yet. And so I got my second degree, and JPL came to Georgia Tech for a career fair, and that's actually the first I had ever heard of this center that built the little Pathfinder rovers and other things in history. And so I drooled all over everybody they would let me talk to, and I got hired in 2000. And in the 19 years that I've been at the lab, I've had the very great privilege of working on a bunch of different missions. I love that at the lab, there's so many things going on that you can change from mission to mission without ever having to leave one company. And so I spent my formative engineering years working on a mission called the Mars Reconnaissance Orbiter. I joined it in 2001, about 4 years prior to launch, and really learned what we mean by systems engineering from working with the team on that mission. And I'll tell you some more about that later. We launched in 2005, took about 6 months to get to Mars, and then successfully got into orbit. I stuck around a little bit more in operations before I left to join Kepler. Kepler, I only spent 2 years of my career working on, about 1.5 years before launch and a couple months after launch. And I know we're not going to talk about that mission here, but if you haven't heard of that mission and all of the planets that it has found and the way it's revolutionized our understanding of exoplanets in our Milky Way galaxy, do yourself a favor, go home and Google that and prepare to be amazed. And then I left to join the Juno mission in 2009, about 2 years before launch. And I wound up spending way more of my life than I thought I would on that mission. 9 whole years. It certainly went by super fast. 2 years leading up to launch, so we were pretty busy for that. 5-year journey to get that spacecraft all the way out to Jupiter. And a lot of people ask me, well, weren't you guys bored? Like, what were you doing? There were so many things going on that we had to do in order to make sure the spacecraft was on the right trajectory to get there. A whole bunch of things didn't go quite the way we expected them to. And so those of us who are involved in something we call anomaly response, figuring out what went wrong, why did it go wrong, what do you do about it, we had lots and lots of fun on that mission. Got successfully into orbit on July 4th, 2016, and has really been revolutionizing our understanding of that gas giant. So if you haven't heard of Juno, go Google it and look at all the really cool things from there. Psyche is a mission that I joined in 2018, and we're going to be spending all the rest of the time talking about that one, and so I won't give you any details yet. We'll wait for it. But first, I want to point out that I am an engineer, but I'm going to spend the next part of my talk talking about the science. Why would I do that? The reason why we send these spacecraft where they're going is to learn more about our solar system, to help us understand what's going on, how our solar system formed, how we all got here. And I love that the lab encourages engineers to learn about science. This is actually me standing with a couple of other engineers in a geology for engineers class that was taught by a couple of Mars scientists who took us all out in the arroyo behind the lab and were showing us the kinds of things that they, as geologists, would be looking for if they were doing a field exploration of a site, whether on Earth or on Mars or on some other planet. And the reason why they do that is because when we as engineers understand what it is that the scientists are trying to do, we will do a much better job of building the instruments to get them the data that they need, and building the spacecraft to support the instruments to get them the data that they need, and sending the spacecraft where they need to go. And so when I joined Psyche, I really jumped at the chance to learn more about asteroids, not just from absorbing the details that our science team was putting together for the mission, but I actually got to sit down and pick the brain of our principal investigator, the lead scientist on our mission, Lindy Elkin-Stanton, who is the director of the School in Earth and Space Exploration at Arizona State University. And she talked me through all the details of asteroid formation and what we think Psyche is like and what we hope to learn when we get there. It was super exciting. So I'm going to pass along some of those things to you to give you an understanding of where this asteroid Psyche fits in with the rest of the asteroids that we know about and what we're hoping to learn from this particular asteroid. So let's start with a very, very big picture, how our planetary systems formed. So in our Milky Way galaxy, there are these giant clouds of dust and gas called nebula. They're made up of hydrogen and helium left over from the Big Bang, and some heavier elements that are put out there by supernova, stars that have exploded. So this is an example. This is the Eagle Nebula, a really zoomed in version of the heart of the Eagle Nebula, which is called the Pillars of Creation. It's an active star-forming region that hides newborn stars in these columns of dust and gas. Now, it's a false color image, but the different colors represent different molecules. Like the blue represents oxygen, the red is sulfur, the green is nitrogen and helium. And these pillars are bathed in this really intense UV light from stars that are right outside the frame. And those winds are slowly eroding these columns of dust and gas that are there. So how do these clouds of dust and gas form new stars? Well, it's thought that when you have a nearby stellar explosion, that creates a shock wave that initiates the collapse of these clouds. And it also injects a lot of different materials into the clouds, especially a radioactive isotope aluminum-26, which you're going to hear a little bit more about later. So this is an artist's conception of what one of these protoplanetary disks would look like, kind of a collapsing cloud of dust and gas that's coming together to form a star in a planetary system. We can't look back in time to our own solar system to see what it looked like back then, but we can look out into our galaxy to find other protoplanetary disks that are there. So what's happening is, as this cloud is collapsing, the angular momentum, the spin, is conserved, so it starts turning faster, and it ends up tending to flatten out. And as it cools, material starts collecting together and condensing out into clumps, which come together first under electrostatic forces and then under gravity as it gets bigger. And as the density increases, if you have enough mass in the middle, it will start nuclear fusion and ignite, and that's when a star is born. And when the star is born, it creates a stellar wind that blows away the residual dust and gas that's there, leaving behind those clumps of material, planets and asteroids and comets that form a planetary system. So in our solar system, the very first asteroid was discovered in 1908 by this lovely gentleman, Giuseppe Piazzi, in Palermo, Sicily. He was actually trying to make a star map, and he noticed something that looked like a star that was moving against the background of the stars. And it wound up being named Ceres, after the Roman goddess of corn and harvest. And later observations let them see that it was actually a lot smaller than other planets. It was about a little under 1,000 kilometers in diameter, so it couldn't really be one of the major planets. And a year later, in 1802, William Herschel came up with the term asteroid, which just means star-like. But a lot of scientists still refer to them as minor planets. You might know that Ceres, this is what it looks like from close-up images taken by the Dawn spacecraft that visited in 2015. In 2006, Ceres was reclassified as a dwarf planet, but I still think of it as the largest asteroid there is in the main asteroid belt. So what are asteroids anyway? I talked a little bit about planetary formation and the stuff that's coming together, condensing out of that cloud. What you start off with are these little calcium aluminum inclusions, which are these very, very tiny, fine minerals, so fine that they're too small really for gravity to start making them come together in the beginning. It's really electrostatic forces. Gravity comes into play when things get much bigger, like the size of mountains. You have this very, very common kind of asteroid when you have enough stuff coming together called chondritic meteorites. These are the most common in the outer ring of the asteroid belt. I'll show you what the whole asteroid belt looks like in a little bit. And it's mostly made of clay and silicates. And a nice fun fact for the day is these little inclusions that are in chondritic meteorites, which allow the scientists to determine the age of our solar system, which is about 4.685 billion years old. And then, as you get bigger and bigger and bigger, when things are coming together near the beginning of the solar system, you get more and more and more mass and more of that radioactive aluminum-26 isotope. When you get enough of that gathered together, it creates enough heat that you melt the body that it's part of. And when it melts, the things that are denser and heavier sink towards the middle because of gravity, and that's why you end up with sort of an iron core. They call this being differentiated. When the heavy things sink in the middle, the light stuff, the rocks and silicates float to the top. That's what happened to our planet. That's why we have an iron core in the middle of the Earth. And deep in the core, where the metal collects, is where we get iron meteorites. Those are asteroid types M, and chunks that fall to the ground on the Earth are called meteorites, made of nickel iron, mostly, and they're mostly in the middle of the asteroid belt. And then you have the S-type asteroids, which are achondritic stony, and those come from that outer part of differentiated asteroids like this. And they have silicates, some nickel iron, and they sort of dominate the inner part of the asteroid belt. And this is just cool, I'm throwing it in there because I really like them. I actually didn't know until Lindy told me about this, that on the interface between the melted metal core and the kind of more rocky mantle, you get this halloysite. It's actually a metal matrix that has giant well, like centimeter-sized olivine crystals in it. Really, really super gorgeous. And when you cut and polish it, you have this lovely polished metal surface with this almost stained glass-looking olivine in it. And we'll hear a little bit more about that. There might be some of that on Psyche, which would be super cool. So the main asteroid belt, where is it? It's out here between the orbit of Mars and Jupiter. Mars is like 1.5 times the distance of the Earth from the sun, so 1.5 AU. The main asteroid belt is between 2.2 and 3.3, roughly, distance from the sun. The estimated number of asteroids is huge, like 1 to 2 million that are bigger than 1 kilometer, estimated. We actually know about roughly 840,000 asteroids. And that sounds like a lot, like a huge number. You would think there would be an enormous amount of mass trapped out here. But the thing that I found is super weird is Ceres, that first asteroid that was discovered in 1801, the pretty big one that's like 1,000 kilometers across, a little bit under that, from here to Salt Lake City, Utah, to put it in perspective. That single asteroid has about a quarter the mass of all the asteroids in the asteroid belt. And if you took all those asteroids and mushed them all together, they would be about a fraction of the mass of our moon, like 4 or 5% the mass of our moon. So it's not that much mass, and it's scattered around this huge, huge region. I'll know that when you watch movies or TV shows and you see images of things going through the asteroid belt and you have the spaceship that's trying to fly around and like get around the asteroids because they're gonna run into you. Yeah, no, it's not really like that. The asteroids have an average distance between them of about 1 million kilometers, which is roughly 25 times the surface of the Earth, or the circumference of the Earth. So they're quite far apart. So a little more about Psyche, specifically the asteroid. It was discovered, it's the 16th asteroid discovered, which is why it is 16 Psyche, in 1952 by Annibale de Gasparis in Naples, Italy. And I think it was discovered, March 17th, 1852, and he was the director of this observatory when he found it. They named it after the Greek mythological figure of Psyche, who was wedded to Eros. And if you know the mythological story, she was married to Eros. There was this whole brouhaha. She wasn't supposed to look at him. She did. She dripped some wax on him and made him sick, blah, blah. And so Aphrodite, who was his mother, wanted to put her to death for robbing the world of her son Eros. But Zeus took pity on her and turned her into, or granted her immortality. So she became one of the standard mythological figures. And when they named it after her, back then, when there weren't that many asteroids, they gave each one an individual symbol. And the symbol for Psyche is this little asterisk, which represents a star, and this little half circle, which represents a butterfly wing, which was the symbol for Psyche way back in the day. Now, Psyche, the Greek term, means soul, which I think is a lovely coincidence when you hear a little more about what scientists think the formation hypothesis of Psyche is. So what is Psyche like? This is an artist concept. We don't have very good pictures of it since it is so far away and so relatively small. First of all, how big is it? It's the largest M-type asteroid, but it's not super huge. If it were a perfect sphere, its diameter would be about 226 kilometers, which is a little more than the distance between Los Angeles and San Diego. So it's a good size in terms of like cities, but it's not super huge compared to Ceres. And it's near the edge of the asteroid belt, about 3.3 AU, and it rotates on its axis once every 4 hours. So its day is 4 hours long, but since it's all the way out there, it takes 5 Earth years to go all the way around the sun. Pretty long year. Earth-based observations give us some insight into things like how dense is it? It bounces off radar pretty well. It has a high thermal inertia. The rates at which it changes temperature. And so scientists think, based on the observations that we've had, that maybe it's mostly metal, mostly nickel iron, and not very much silicate. But those Earth observations have a lot of uncertainty, and as we study them with telescopes, we learn a little bit more, and it kind of changes what we understand about the asteroid. So we don't really know exactly what it's like, and we're hoping that this mission will show us. And one of the things I love about our science team is we have science team meetings about once a quarter, and they talk not just about the science measurements they're planning to take at Psyche, but their understanding of the measurements that scientists on Earth are taking of it. And it's kind of cool when they come up with facts that don't quite fit in with the current theory. You don't hear the scientists go, well, that sucks. Like, we're not going to believe that fact because it doesn't fit. They say, well, that's great, because when you find places where your idea of how things work don't match up with the actual observations that you make, now you know that's definitely a place where you're going to learn something. That's like a gold mine in terms of science. And so all the scientists are getting more and more excited to learn exactly what that asteroid is going to be. So this, I've been saying that it's a little bigger than Los Angeles and San Diego. This is just to kind of give you a sense of what it looks like against California. And you can see a little bit of sense of what it looks like against Arizona, since that's where our PI is from. It kind of fits between Phoenix and Flagstaff. And I put Massachusetts in there as one of the smaller states too. If you lop off this crooked end, Psyche is about the same size as that. And then to compare it with some of the other asteroids that we have visited with spacecraft over the years. I mentioned Ceres, which is the largest asteroid out there, about 950 kilometers across. This is Vesta, which is about 530 kilometers across, a little more than half the diameter of Ceres. And this is the Psyche shape model compared to it. So now I'm going to switch gears a little bit and tell you some about Psyche, the mission, the spacecraft that we're actually sending all the way out to go and visit this really cool asteroid. A lot of people are curious to know, how does NASA select missions? Who decides what missions we're actually going to fund and do and which ones we are not? There's a bunch of different ways, and one of them is through this process called the Discovery Program. And the way it works is this. Every couple of years, NASA puts out an announcement of opportunity saying, these are the science goals that we're most interested in our strategic plan. This is your cost cap. Okay, NASA centers often pair up with industry partners like Lockheed Martin or Ball Aerospace or Orbital or Maxar, and then come up with a concept for a mission. And then they select them. In the year that Psyche was going through this process, there were 28 different proposals that were all trying to get selected and made into real missions. After the step 1 process, NASA down selected to just 5, and then they had time to go in and do a little bit more work and fine tune the things that they're doing, and then NASA finally selected just 2 of those to become real missions. One of them was Psyche, and one of them was Lucy. And it was very, very exciting for the team because most missions have to go through this process multiple times, right? 2 out of 28, those are not awesome odds. And so you don't get selected and you're sent back to the showers, you wait for the announcement to come out, you try it again, and you keep fine-tuning and fine-tuning and fine-tuning your proposal. Sometimes things go through this multiple times before they get selected. Psyche made it through on the first try, which is almost unheard of. I only joined the mission after it got selected, and so I was very proud of those people for doing all of that work so that I could join this cool mission and be a part of it. So this is just a sample of some of the partner institutions. Sometimes also people think, well, NASA is sending a mission to somewhere, so it's just NASA doing all the work. But you usually have somebody who's partnering with NASA, sometimes to build the spacecraft, a lot of times to build the instruments. Our scientists come from different institutions. It takes a whole village of people in order to put together a mission like Psyche. Now I'll tell you a little bit about the life cycle of a project. What actually happens when a mission is in the process of getting selected and then gets selected? How do you go through all the steps of getting it built? So first, you have that concept study that I was talking about, especially if you're something that's going through a phase A. And you do a high-level design. What's the spacecraft going to be like? What are your science objectives? What kind of instruments are you going to have? Are you going to do a flyby? Are you going to go into orbit? Can you observe something from Earth? Those kinds of details. And I say high level, but it's like a 1,000-page document that they put together that has details on what the mission is going to be. And then if you get selected, you go into phase A and then phase B, which is where you do your preliminary design. And that's where you're really fine-tuning even more details about what your design is. You're making some of those trade-offs. How much power is going to be allocated to the different things? How much mass can you have? Making lots of choices like that. And then you go through a very scary thing called the preliminary design review. And that's where you would have different people representing elements of the mission stand up in front of a room like this size with maybe a dozen very senior review board members whose job it is to listen to all the things you're telling them about the details of your design and poke holes in it, find problems with it. Not because they're mean or they just want us to feel bad, but because they're trying to help us find the areas where we might have trouble later so we can go tighten down those things and have a stronger mission going forward. And then you do even more detailed design, which is called our critical design and build. You're starting to build test models, building prototypes to make sure everything is going to work. Psyche is actually in this phase right now, and soon we're going to have our critical design review, where even more detailed review boards trying to poke holes and find issues of things that you can go and fix. Then you move into what we call integration, testing, and launch. Now you have your flight hardware, and you're starting to put it all together, and you're testing it along the way. Because once you launch one of these spacecraft, it's going to go millions of miles away. You can't exactly send someone to whack it with a wrench if it's not working. And so you test and test and test and test it, and then you strap it to the top of a rocket that you really hope those people did a great job building, and then it's on its merry way to where you're going. The first couple of months after launch is still considered part of this, maybe 30 days, and your checkout before you officially enter your operations phase. And that lasts from the time that you are on your way during cruise to your destination, and then when you get to your destination and you're doing your final orbital operations. So there's a lot of stuff that we're doing all along the way. And if you think about it, there's so many different kinds of engineers and scientists and mathematicians and many other people who are required to make a spacecraft work. I'm a systems engineer. I promised I'd tell you a little bit about what that term means. And it's kind of like this. When you're building a spacecraft, you need it to be able to communicate with the Earth, so you have a telecom system, which has antenna and amplifiers and radios. You need it to be able to collect power, so maybe it'll have solar arrays and a battery and ways to get that power around on board. You need it to be able to control its attitude, so you might have reaction wheels and thrusters. There's all of these variety of things that the spacecraft needs to be able to do, and there are people who focus on those different areas. But a flight system engineer is someone who makes sure all those different parts of the spacecraft are going to work well together, and that you don't make a design decision in one area that winds up causing you trouble in another area. So we're sort of the glue that holds everything together. And when something's not working and we have to figure out what to do about it, we have to pull together the right experts, ask the right questions, turn over all the rocks, see all the pros and cons of all of our different options, and make sure we choose the one that's going to be best for the spacecraft. Not just technically. Sometimes we also have to think about cost and schedule because we don't have infinite of those resources. And then a project system engineer is making sure that the spacecraft and the instruments and the ground data system and the trajectory design and the launch vehicle, all of those things are working together. So as a project system engineer, that's where I sit, working with all the different teams to ensure we're going to design and build and test and then operate the spacecraft so that it works and gets all the way out to Psyche and gets the scientists the data that they need in order to answer their science questions. So what are our science questions exactly for Psyche? Well, we would like to know, is it a core or some other kind of melted material or some other weird thing that the scientists can't even imagine how it would happen, some kind of primordial unmelted metal? And the science instruments are designed to be able to help us tell the difference between those things. They want to know what are the relative ages of the surface regions, basically by counting the craters that are there. And you can tell by whether craters are on top of other craters, which ones happen first or last. And so we'll be able to figure that out. We want to know, how much sulfur, potassium, silicon is there on the surface, and several other kinds of components. And we have an instrument that is specifically designed to do that. You'll hear a little more about that one. We want to know if the formation was more oxidizing or reducing than the Earth's core. And we also want to characterize the topography. What does the surface actually look like? When you think about craters on Mars or craters on the moon, you kind of have a sense of what that looks like, craters in rock, right? If you have this thing that's mostly made of metal, and then you have another thing slam into it and melt the metal to splash it up, and then it freezes in place, what does that look like? We have people who are firing little metal slugs at iron ingots in order to get a sense for what craters might look like on the surface of Psyche. I mentioned palisite, which would have these olivine minerals embedded in a metal matrix. If our theory of how Psyche formed is correct, maybe it'll have palisite, glittering palisite on the surface. And you'll see a little bit more about that on the next slide. So this is kind of a story of how the scientists think Psyche might have formed. If it is the little core of a baby protoplanet, maybe it was formed something like this. It starts off by a differentiated object that got big enough to have enough radioactive aluminum-26 isotope to get hot enough to melt and have the metal sink toward the middle. And then maybe it had a collision, maybe not one, maybe a series of collisions with other things that knocked all the rocky outsides off, and then the metal came back together under gravity. And then as it started freezing, maybe it froze from the outside in, maybe it froze from the inside out, we don't really know, but if it froze from the outside in, then maybe as it shrank, you start to kind of increase the concentration of different liquids inside, maybe some sulfur-rich liquids that would float to the surface. And as it continued shrinking, the metal might crack and release areas where this sulfur could spew out on the top, little sulfur volcanoes. And it could have started forming this magnetic field because it's got this molten metal here. And then as it continued to shrink, you might have had the sulfur just freeze out on the top. Perhaps something came along and knocked it on its side, because we do know that its axis is not straight up and down. It's kind of rolling on its side around the solar system. And it could look like this, with this remnant magnetic field, with these deposits of sulfur on it. And it does look like it has a couple of pretty giant craters as far as we can tell from the Earth. So this is the story of how Psyche might have formed. It could literally be the heart of a protoplanet, which is why I love that the word Psyche in Greek means soul. It's kind of cool. I didn't even know that way back in 1852. And so our mission design, how are we going to get the spacecraft out there? This is the sun. This is Earth and Mars. I left out Mercury and Venus just so it wouldn't get too cluttered. And Psyche is out here. Its orbit is a little bit eccentric. It's closest to the sun is like 2.2 AU, farthest away is like 3.3. But it's out here in the main belt between Mars and Jupiter. We are going to launch a spacecraft in August of 2022. It's going to go out past Mars to get a gravity assist to boost our speed, our velocity, and then we will arrive at Psyche in January 2026. We'll orbit the asteroid for 21 months, doing our science observations, and then the mission will be over in October of 2027. And we are using solar electric propulsion to get there instead of the more typical chemical propulsion. I'll say a little bit about what that means. So our spacecraft is about the size of a regulation-sized single tennis court. It stands as tall as a basketball hoop, and the body is about the size of a garden shed. It weighs roughly 1,600 kilograms dry, but we're gonna load it up with 1,000 kilograms of xenon to use as its propellant. It's the same xenon gas that you see in those really cool kind of blue gas headlights that you see. This is the most xenon gas that has ever been loaded onto a spacecraft before, so that's kind of cool. It's using xenon Hall thrusters, and this is kind of cool because when you think about a giant spacecraft, you imagine you have to have a lot of thrust to get it going. But electric propulsion spacecraft don't work like that. They use a very small amount of thrust, but they just keep thrusting and thrusting and thrusting and thrusting. So you build up acceleration over time, and you use that to get going fast enough to get to where you're going. If you take a slice of bread and stick it in the palm of your hand, that's how much thrust our solar electric propulsion engines make. It's just not very much, but they have to be on all the time. JPL is partnering with a company called Maxar, formerly SSL, but now Maxar, who has built a lot, many comm satellites in orbit around the Earth, and they do a lot of electric propulsion missions. So we're taking advantage of their expertise. They're building most of the structure of the spacecraft, the power system, including the arrays, and the electric propulsion system. JPL has done lots and lots and lots of very deep space missions. This is going to be Maxar's first deep space mission. And one of the hardest things about deep space missions is that the spacecraft is so far away, it takes a long time to communicate with them. It might be like half an hour before a signal gets all the way out to Psyche at its farthest distance, and then half an hour before it gets back. So the spacecraft have to have a lot of smarts on board to be able to deal with unexpected situations and keep themselves safe until the ground can get in the loop. And so JPL is doing the avionics, the computer, the software, and the fault protection. Fault protection just means something goes wrong, the spacecraft takes some pre-programmed actions to keep itself safe until we can get to it and make sure that it's okay. The spacecraft is very big, and the solar arrays produce a lot of power. At Earth, they would produce something like 20 kilowatts of power, but when you get all the way out to Psyche distance, it's going to be closer to like 2.3 kilowatts. This is another view of what the spacecraft looks like with a person thrown in there for scale, and it also lets you see where the instruments are. So one of the things we're going to try to do is measure the magnetic field. You saw those purple lines around the asteroid in that storyboard that I had shown you before of the formation of Psyche. So we have these magnetometers that are going to be there to measure that magnetic field. We have to put them way out here on a boom because the spacecraft, because it has electricity going through it, generates a small magnetic field of its own. We need to get them away from that so it doesn't interfere with the measurements that they are making. We also want to measure the composition of the surface. Are those really sulfur deposits out there? How much nickel is there? How much iron? All of those different elements. So we're doing that with a gamma ray and neutron spectrometer, also on a boom. The spacecraft has some amount of nickel in it, and nickel is one of the most important elements we're trying to measure. So we need to get it away from the spacecraft so it doesn't interfere with its measurements. We have imagers on board. They're going to take pictures of the surface so that we can study what it looks like and also get a sense of what it's composed of. Another cool thing about our imager is it's not just an instrument for science, we're also using it as an engineering component. Psyche is a small asteroid, well, it's not a planet. It's small enough and far enough away that we can't tell precisely where it is to the point where we can navigate all the way there just using the information that we know from the Earth. So actually, as we get closer to it on approach, we're going to take images of it, send those images back to Earth, and the navigators can compare where it is versus the star field and tighten up our understanding of where it is in an approach that we call optical navigation. We're also doing something called deep space optical comm as a demonstration. We're using an X-band radio to communicate with our spacecraft, which we've done on many, many missions in the past, but we're demonstrating the use of lasers to communicate back to the Earth. That actually has been done in Earth orbit, but it hasn't been done past Earth orbit. So we're going to demonstrate it all the way out to the orbit of Mars. And the exciting thing about that is when we show that it works, you'll be able to use about roughly the same amount of mass, power, and volume and multiply your data rate by 10 times or up to 100 times for missions that need to send back lots of data. So we're going to launch a spacecraft in August 2022. This is an artist's conception of what the spacecraft is going to look like. We deploy the arrays shortly after launch and get them on sun so that we can power the spacecraft. We have a 90-day checkout period to make sure all the engineering components and all the instruments are working just fine as we're on our way. We're going to start the demonstration of the deep space optical comm. There's an observatory in Table Mountain in California and also Palomar in California. We're going to uplink from Table Mountain with a 5 kilowatt laser beam all the way up to the spacecraft, which I think is super cool, from a 1 meter diameter antenna to a flight laser transceiver on board, which has a photon counting camera that'll then be able to decode the information that it's getting from the uplink. It'll lock onto that laser beam and use it in order to direct the laser beam that it sends down to the ground to this collector, which is a 5 diameter telescope at Palomar, and there's a photon counting camera on the bottom here at this telescope that can then decode the information that's sent back. So it's kind of cool communicating via light. To me, that seems a little more Star Trekian than some of the things we've been doing so far. I'm excited about that. So when we get all the way out to Psyche, I mentioned the fact that we're using our camera to do optical navigation to pinpoint exactly where the asteroid is so that we can safely get into orbit. When we do that, we're going to go into this pretty big orbit at about 700 kilometer altitude to start the science. We're going to hang out there for 56 days, about 41 orbits all the way around, and we'll be able to do our magnetic field measurements and take images and do mapping of the surface. And then after that, we're going to spiral down for a couple of weeks to get to this closer orbit of orbit B, which is 290 kilometers altitude. We're going to hang out there for about 80 days, and that's where we should really be able to meet our science objectives for mapping and the topology, and continuing our magnetic field measurements. If we're lucky, we'll be able to detect a remnant magnetic field all the way out at orbit A, and we'll all have a party, but then we'll go back to work and keep doing the rest of the mission. And then we spend about 3 weeks spiraling down even closer to orbit C, which is an altitude of about 170 kilometers. We'll hang out there for 100 days, and that's when we ought to be able to get really, really good gravity science measurements using our telecom system, because the gravity of the asteroid will perturb the motion of the spacecraft, and we can use that change in Doppler signal when we're getting the radio signal back on the ground to learn about the gravity field. And then we're going to spend quite a long time, like 20 weeks, changing our orbit to get to this vastly different orbit that's at 160 degrees inclination, and our lowest yet, just 85 kilometers. And that's one of the reasons why we need to use optical nav to know exactly where that asteroid is so we can get close to it without being in danger of bumping into it. We'll be there for 100 days, and we need to be that low in order to use our gamma ray and neutron spectrometer to get the measurements of what the surface is actually made of. So that's how we'll do the science. Now, I wanted to put in this video for you guys. It's an artist's conception of what it might sort of look like if you're riding along with Psyche, the spacecraft, heading to 16 Psyche, the asteroid. You can kind of see these two huge craters that I talked about. You can see this discoloration on the surface, which might be where that sulfur-containing materials was laid down once it squished out of the asteroid as it was shrinking and the surface cracked. A really cool feature that was put in here by the artist after talking with the scientist is that as the metal is shrinking, you might get these huge, long, super high cliffs where the metal cracked. So it could look like, if you were able to go there and like do really cool base jumping off of the cliffs, that'd be super awesome. You can see all these craters all over the surface that we'll be counting and using in order to determine the relative ages of different regions. And then it's kind of hard to see as it goes by. Maybe we can catch it. They also put in this depiction. You can see where it's a little bit shiny, sparkling in here, where there might be some palisite on the surface, right there. And these might be huge metal spikes where you had something crash into it and the metal melted. There's the sparkly stuff, where you had metal melt and then splash up and then freeze in space. So we don't actually know what Psyche is going to look like, but it's cool for us to talk with the scientist and get a sense of it, and then have the artist gen up depictions like this. But one of the things that our principal investigator is fond of saying is that it's definitely going to be way different than what we could imagine, so we're all looking forward to it. One last thing I wanted to throw in there is that our project does a really great job, I think, of reaching out to people and getting them excited about Psyche in not necessarily traditional ways. We have this Psyche-inspired art program that brings undergraduate students from any discipline or major together to help share the excitement of Psyche by coming up with artistic and creative works, like this clay vase that has some things on the surface of Psyche, like this painting that was made, and I think this is cross stitch over here, and I really like that one. It's actually Psyche, the mythological character. So this is just a couple of links for you to look at while we go through Q&A, and I'll be happy to answer questions that you might have about the mission.